The world's largest hydropower project already exists. It's called Three Gorges. China is now building something 3 times bigger, inside the Himalayas, on a river shared with 2 other countries. This is the Great Bend, and the stakes are enormous. What if a single bend in a river could power an entire country? And what if that same bend could quietly reshape politics, safety, and trust across half a continent? High in the Himalayas, a river drops like a cliff. China has decided to turn that drop into electricity at a scale the modern world almost never attempts. This is the story of the Great Bend, a place that looks like geography until you do the math. In late 2024, China approved one of the most ambitious infrastructure projects in human history. Not a megacity, not a space program, a hydropower system hidden deep in the Himalayas, in a region most people couldn't find on a map. Then in July 2025, Beijing made it official. 5 massive hydropower stations, 1 river, an investment of about 1.2 trillion yuan, roughly 170 billion US dollars, a projected electricity output of 300 billion kilowatt hours every year. That's the kind of output you normally associate with an entire country. China says it's clean energy. China says downstream impacts will not be significant. India and Bangladesh are watching very closely. This project sits upstream on a river that becomes the Brahmaputra, the lifeline of tens of millions of people. So today, we're asking 3 simple questions. Why is this one bend in a river so powerful? How can anyone even build something this large in the Himalayas? And what decides whether this becomes a clean energy monument or a permanent regional headache? Everything about this project begins with gravity. In Tibet, the river is called the World. Downstream in India and Bangladesh, it's known as the Brahmaputra. For most of its length, it behaves like a normal river, until it reaches the mountains. Near the Namcha Barwa Massif, the river makes a violent U-turn known as the Great Bend, then plunges into one of the most extreme river corridors on Earth. Here is the number that changes everything. The river drops about 2,000 meters in roughly 50 kilometers. It behaves like a controlled freefall. In hydropower, height is everything. A river flowing across flat land is like a parked car. A river dropping 2 kilometers is that same car rolling downhill with no brakes. Every liter of water carries stored energy, and here, gravity never stops working. That's why engineers look at this bend and see something rare. A natural battery. When people hear hydropower, they imagine one massive wall of concrete. China is building a cascade. 5 hydropower stations stepping down the river corridor. Each station takes part of the drop, spins turbines, then hands the water to the next station. Think of it like a staircase made of gravity. Each step extracts energy without stopping the river completely. This design matters for 2 reasons. First, efficiency. You don't need a giant reservoir when the height difference does most of the work. Second, control. A cascade behaves like one coordinated system. Release timing, seasonal rules, emergency response. Everything is connected, and at this scale, operations matter as much as construction. Now comes the hard truth. This river does not flow through flat land. The Yarlung-Tsangpo Grand Canyon is steep, narrow, remote, and hostile to construction. Weather changes fast, slopes fail. Access is difficult. Even in recent history, parts of the region were isolated. One place often mentioned is Maydog County, which only gained reliable road access in 2013. So the challenge goes beyond building a dam. It becomes a question of building 5 giant hydropower stations tied together by tunnels inside mountains in one of the most geologically aggressive places on Earth. For most countries, the answer is simple: no. For China, the answer depends on something very specific: machines, techniques, and experience that almost no one else has. This is the constraint most people skip. The Great Bend is 3 major projects stacked together. First, extreme mountain tunneling. Second, underground power plants the size of cities. Third, ultra-long-distance power transmission out of the Himalayas. Individually, other countries can do part of this, but China is the only country that has proven it can do all three at once at this scale. With recent real-world projects, the limiting factor is capability. The most important machine in this entire story is the tunnel boring machine. In terrains like this, the job is tunneling straight through the mountain. You build through them. China has already proven it can do some of the most extreme hard rock tunneling on Earth. The best example is the Jinping 2 hydropower project. Jinping 2 diverted a river bend using 4 parallel headrace tunnels. Each tunnel is about 16.7 kilometers long. Each has a diameter of roughly 12 to 14 meters. But the number that matters most is above the tunnel. The rock overhead, called overburden, reaches 2,525 meters. That is more than 2 kilometers of mountain pressing down. The rock stress reached 100 megapascals. Water pressure reached 10 megapascals. That combination destroys ordinary tunnels. High stress squeezes the tunnel shut. High pressure turns cracks into jets of water. China overcame this using massive hard rock TBMs, advanced rock reinforcement, high-pressure grouting, real-time monitoring, and decades of experience dealing with rock that does not behave politely. This matters because the Great Bend requires the same class of engineering, possibly more, and China already knows how to do it. Even if you can move the water, you still need somewhere to put the turbines. At this scale, the powerhouse is carved into the mountain. Whole complexes go underground. A clear reference point is the Baihetan hydropower project, one of China's newest mega dams. Baihetan includes an underground system with 364 caverns, about 25 million cubic meters of underground excavation, and a total tunnel length exceeding 200 kilometers across the project. This is an underground world. Inside those caverns are turbines, generators, transformers, access halls, and control rooms, all protected by hundreds of meters of rock. Why underground? Because underground structures are more stable, better protected from weather, and easier to integrate into narrow valleys. So when China says 5 cascade stations at the Great Bend, this is what it implies. 5 underground power systems of extreme complexity, repeated, coordinated, and operated as one machine. When big dams fail, it usually starts with water you can't control. Turbines are rarely the problem. That's why Chinese mega projects are designed with enormous discharge capacity. At Baihetan, maximum discharge capacity reaches over 42,000 cubic meters per second. That capacity comes from multiple spillways, multiple deep outlets, and multiple discharge tunnels. This is deliberate redundancy. In the Himalayas, the worst case is heavy rain plus landslides plus earthquake shaking. The only defense is the ability to move water fast and move it safely when nature surprises you. Now we reach the hardest part. The Himalayas move. The 1950 Assam-Tibet earthquake reached about a magnitude 8.7, one of the strongest earthquakes ever recorded on land. Earthquakes here can do more than shake buildings. They trigger landslides, they block rivers, they create sudden flood waves. So how do Chinese engineers cope? They design for controlled survival. At Baihetan, engineers evaluated rare shaking levels with bedrock peak ground acceleration around 0.46 g and even higher extreme checks near 0.54 g. That's close to half the force of gravity. They used 3-dimensional nonlinear simulations, dam foundation interaction modeling, dynamic testing, and dense sensor networks. They simulate the dam, the mountain, and the water as one system, then monitor it continuously. This is modern mega engineering built on data. Even if the Great Bend generates 300 billion kilowatt hours per year, that power is useless if it stays in the mountains. This is where China has a clear, proven edge: ultra-high voltage direct current transmission. China operates world record UHVDC lines. One flagship example transmits 12,000 megawatts over 3,000 kilometers at plus or minus 1,100 kilovolts. That's enough to move the outlet of multiple large power plants across an entire continent. Very few countries can do this. China already does, routinely. So the Great Bend is a generation-plus transmission system designed to move energy from the hardest places to the biggest cities. Even with all this engineering power, downstream countries focus on one thing: time. The Brahmaputra basin already floods during monsoon season. Rainfall in the mountains can surge into the river system fast. For downstream communities, a warning that comes late is a disaster. That's why India and Bangladesh focus on operating rules, release timing, notification systems, emergency procedures. Engineering can manage risk. Trust manages fear. So what is the Great Bend Project really? It's a test of whether modern engineering can tame extreme geography, a test of whether the world's most ambitious hydropower system can operate safely in an earthquake zone, and a test of whether transparency can keep pace with scale. China has shown it has the machines, the technology, and the engineering capacity to build this. Very few countries could, but in a river that crosses borders, engineering is only half the story. The other half is predictability, because the real power of this river goes beyond electricity. It's what happens when gravity, technology, and trust all meet in the same place.